will start with the coalgebraic walk. I'm from the Ministry of Coalgebraic Walks. This is an overview of my talk. So I'll talk about walks mainly, and this will lead to some theory and actually to some coalgebraic modeling of quantum computations, and also come in and have a seat. Want to come in, do join. And will also lead to a description of Turing machines. So my aim is to look at quantum computation. This is a topic I've been looking at for at least a year, and especially in connection to standard forms of computation like deterministic, non-deterministic, etc., which are usually described in terms of coalgebras, and it has been an obvious question for some time already, a question that also Samson here worked on, how to model these kind of quantum phenomena coalgebraically. I think I have a reasonable answer by now, which I'd like to present to you, and also as a byproduct I'll describe how to capture Turing machines coalgebraically, and this has been a long-standing open problem in the coalgebraic community. Okay, so, but walks on the line will be my example. So why coalgebras? They have emerged as a general formalism in state-based computation with their own advantages. I'm not going to use it very extensively. There will be some other talks about this later this afternoon. But the interesting thing is that the language of quantum mechanics is very related to the coalgebraic language. So people talk about states and observations, and observations disturb the state or have a side effect, that we even have serious philosophical issues in this area which have to do with the kind of computation involved. One slide about coalgebras. They're models of state-based computation. Typically you have a state space X, you have a map on it, a transition map going to f of x, where f is a functor which describes the type of computation. So here is an example for a deterministic automata, and look here, you have some structure on the right hand side, which is your f, and the coalgebra map consists of two parts for doing a next step and for checking whether a state is final or not. If you want to cover non-deterministic automata, you simply change the functor involved. You put a powerset here so that your successor states will be a set of states and not a single state. You can even replace this functor powerset by a distribution functor, and then you suddenly move into probabilistic computation. So this is a very flexible generic framework which allows even to prove various results for a general functor. I will be especially interested in coalgebras of this form T of x, where T is a monad. If you don't really know what a monad is, then just ignore this, it's not so very important. But one specific point is that the set of coalgebras forms a monoid on the Kleisli composition, so you can compose these kind of things. A bit more technically, it's a monoid in the category of T algebras, which is something which gives some extra structure for free. My main examples will be powerset, distribution, and multiset. Now, powerset is fairly well known. The distribution monad can be described like this. So d of x on a set x is the set of maps phi from x to the unit interval 0, 1 with finite support, and the support is the set of elements on which phi is non-zero, and they add up to 1. Now such functions can be described more conveniently as convex combinations like this, which is a convenient notation where the support is the xi's, the r'i's are real numbers describing the probability of the element xy, and these r'i's should add up to 1. Coalgebras of this form x to dx are also called Markov chains, and they describe probabilistic transitions. The multiset monad is a variation on this. It's similar and less complex. Now you look at maps phi from x to c. C is the complex numbers. In this case you can put any semi-ring here, but I'm only interested in this special case where the support is finite. And again, you can write these things as formal linear combinations of zi are complex numbers and the xi's are elements of your carrier set. And this M of x describes the free vector space over x then. The coalgebras of this, you can see them as weighted automata, where the weights are in a certain weights associated with the transition are complex numbers. So let's look at walks. I'm looking at walks on a line in two directions, represented by the integers. And I like to look at these three kinds of computations, coalgebraically. So let's look at the non-deterministic version. So my state space is the integers. I look at the successor function, which takes the set of successor states, and I'm looking at the kind of walk where the drunkard can step left or right, non-deterministically, so k goes to the set of both numbers. Now let's repeat this. So if I start in 0, what are the possible successor states? Obvious. If you, in 2 steps, you can reach those 2 places. You can go left 2 times, go left middle. You see that the 0 can be reached in 2 ways. But these 2 ways, you don't distinguish them in this description. You go on like this, and this is the set you get after n steps. Always differences of 2. If you like, you can draw it in a picture like this. So it's clear basically what's going on here. This iteration, if you want to describe it a bit more mathematically, you use the Coalgebraic extension. So remember, S was an operation from Z to powerset of Z, but I extended from powerset to powerset by taking a subset and taking the union of all outcomes over this subset. Now then, the set of successors can be described by iterating this Coalgebraic extension n times on the singleton 0. This is not very surprising, but I'm telling this explicitly because I'll do the same thing in other frameworks as well. And this can be described as iteration directly in the Coalgebraic category if you like, if you like that better. So let's look at probabilistic walks. So now we use the distribution functor here, the d, instead of the power set. In the way, the kind of walks I look at, you can still step left or right, and I take them with equal probability. So this is a formal convex combination, which is in this distribution functor. So let's iterate this now. So starting in 0, I get this. So it's a bit funny, maybe the notation, but it's a formal combination of -1 and 1. So what do you get next? Now the probabilities are 1/4, 1/2, 1/4. And now it matters that you can go in 2 steps to 0 again. This is the next one. And the picture you get is this one. And maybe you recognize the structure already in this. It's of course Pascal's triangle involved. And this is after n iterations starting in k, you get this huge formula. This is a formal convex sum, where these are each time the positions, and this is the probability. And this is indeed a formal convex combination. Because if you add up all these factors here, these denominators, then they are 2 to the power n, which is precisely what you have here. But of course you all remember this from your secondary school days. Again, you have a Coalgebraic extension like this, and the Coalgebraic extension now splits up each factor in a half -1 and a half +1 version. And if you iterate this, you get precisely this formula. So if I iterate this Coalgebraic extension, now this looks a bit funny. This is the singleton set 0. It's a formal convex combination. This is extremely formal, with 0 with probability 1. But think of it as the singleton set. And you get this out. Again, it's iteration implies suggestion. So now let's go quantum. In quantum walks is a fairly large area on its own. And people typically describe computations as endomaps of this form, S to S. And I looked especially at the work of Julia Kempe, someone who published quite a bit in this area. And I will try to give Coalgebraic or even monadic description of this. So we need a little bit of mathematics to understand what this set S is and what these walks iterate. I take M of Z. Remember, M is the multi-set over C. So this is the free vector space over the integers. And I write the base vectors for K an integer in this cat notation. So think of this as the, here is 1 dot K. K occurring just once. And I also need C square. C is the complex numbers again. That's a one qubit space. I'll write, in order to prevent confusion with this, the base vectors as up and down. You can think of an electron if you spin off an electron if you want to. My state space, this S, is then this tensor product. And if you feel a bit uncomfortable on this, just think of these as the base vectors. So it's up tensor K and down tensor K. Now, the way you do quantum walks is like this. So here are the two base vectors on which this operates. And starting in up and a K, I go read it like this to K minus 1 and K plus 1. But I have to put up and down in front to be in the right space again, and a certain probability, think of it, a modulus here. And people who know this a little bit will quickly recognize that in the background I use Hadamard's matrix in how these factors are distributed. Now what is the game? Is we're interested in the probability of reaching K after a number of steps, and starting in 0, and to be really precise in up tensor 0. And how do I get there? Well, you iterate this function, this endomap. Iteration is now very easy. You just compose the function with itself, and you measure in the basis K after a number of iterations. And the probability then is the standard way you do this in quantum mechanics. You take the square of the absolute value of the modulus, that is the amplitude that is there. So let's do this. I start here, and the first step gives me this. Now what are the probabilities? The probability of getting -1, you take the absolute value of this and square it, and it gives you half. The probability of going to 1 is this. It's purely mechanical, but in the next step I iterate this and I apply this function q to this. But this, we're living in a linear world, so I apply q to this and q to that, and then I add up. Gives this. Doesn't matter about the details, but you see -2, 0 twice, and 2 appearing with certain amplitudes. If I look at the probabilities now, I square half, I add half and half up, and I square them, which gives half, and here I square this one, I square minus this, that's the absolute value, and I get 1/4. Okay, now we can iterate again. But it gets a bit hairy now. The next step gives you this, which you can simplify a little bit, but the probabilities now become this. You get 1/8, 5/8, 1/8, 1/8. And you see now it's starting to differ from what we had in the purely probabilistic case. That's a certain, what you could call drift to the left, in this here, which has to do with the interference involved. Interference because you have this plus and minus in all these factors, and if you add them up, this is what comes out. So the tree you get is now this. And you see, this, we computed so far 5818, but if you go down you see that still there's a certain drift in there. And by choosing another matrix than Hadamard's, you can steer this a bit. I think this is part of the area what people do here. But I didn't look really deep into this. Now, there is, in this coalgebraic modeling, there are two, maybe three slides which are important for understanding the underlying mathematics, and this is one of them. There's a basic isomorphism which has this. Remember, this is the state space we're acting on, and I can describe this equivalently as the multiset on x plus x, where plus is just this union of sets. X is an ordinary set. I took previously for x the integers, but it works more generally. And there is the following chain of isomorphism: c squared is c plus c. Plus is here the byproduct.
This is happening in the category of vector space.
Precisely, very good. And so by distributivity, I get this. Now C is the tensor unit, so it becomes this. Now the next step is M is a free vector space functor, so M preserves coproducts. And so M of this will be the coproduct in vector spaces, but plus is also coproduct. So we get this simple description. It's very basic, but it simplifies matters a lot. Because the main theorem now is that endomaps of this form, remember this is the style I used in the beginning, correspond to coalgebras of this form. So this is the coalgebraic description. How does this work? Again, it's fairly straightforward. So we start from these endomaps. This step is the isomorphism from the previous slide. I applied it both ways. Now, this is still in vector spaces. Now, M is the free functor, so I can remove it here, and I end up in sets, z plus z, going to the multi-z z plus z. But having a plus on this side, I can split this in two maps, and I can put the two maps together on the other side, so I get this. Okay. That's very nice. So, quantum computation, quantum walks are coalgebraic, is the claim so far. But, of course, when I got this far, my next question was, is this a monad? Is this also a monad? Because powerset and distribution were monads, so is this also a monad? And this turned out to be the case. I wasn't aware of this, but there is a basic monad transformer result, which is the following. If T is a monad, then so is T maps to n co-power x, and then the whole to the power n. So this is x plus x plus x n times. This is a bit like state transformer monad, but here you have the co-product inside and the product on the outside.
Is that completely general or specific to sets?
No, it's completely general.
Yeah.
Completely general, yeah. So I applied it for T is the multiset monad and N is 2. Right? So the claim is, at least, is quantum walks are coalgebraic or can be described via monads. That makes me happy, given my background and history in this area. Maybe not everyone around, but I think it's a cute result in itself. But it doesn't stop here. So there are actually three representations of these quantum walks. First of these endomaps. This is just a repetition of what I said before, so you don't have to read this if you want. Then there's coalgebras like this. The equivalent description of a coalgebra is like this. I have to make a little bit, so M in here goes to a big tuple, because I have a square here. I have to give two elements. This is the one, that is the other one. But here there's a coproduct. So I have to label things with left or right. So, and I use kappa 1 and kappa 2 for this. And if you look a bit, you can see that this factor becomes here, goes here. This factor, the k plus 1, goes here with the kappa 2. The kappa 2 corresponding to the down arrow. So it's really a reordering of this material. Actually, there's a third description, which is as matrices. 2 by 2 matrices over coalgebras. And this is what I'll describe next. Again, this is the next one slide which contains some essential technical context. M is an additive monad. Basically, what it says, it sends finite coproducts to products. The power set also does so. So M of 0 is 1 and M of x plus y is mx times my. Why is that useful? Well, we were working with these kind of coalgebras. M of this plus becomes a Cartesian product with the square on the outside, so it becomes mz to the power 4. So I have 4 coalgebras of this form. And I will organize them in a 2 by 2 matrix. So I get a matrix of coalgebras. And it looks like this. And if you remember the previous representations, you can sort of recognize the four elements in here. That's just a reordering of material. But what is nice about this is that matrix composition corresponds to endomap composition in the other representation, and also Kleisli composition for these coalgebras. So it's sort of a cute way of redescribing things. One question I haven't worked on, and if you have such a vector representation, you can, or such a matrix representation, you can do various algebraic things, and it's not so clear if they can be done here as well, what they yield. So I'll leave that to the end. Why does this work? The set of coalgebras is a ring with sums inherited pointwise from the vector space structure that you have, M of x, and Kleisli composition as multiplication. And here the result that I mentioned in the beginning, that this was in general a monoid in the category of algebras of the monad involved, it plays a role here in the background. This is a special case. Actually, we have an algebra. Yesterday we saw some talks on algebras. It's a monoid in the category of vector spaces, and we can hence do matrices over this ring and semi-ring. Actually, I only need the semi-ring structure for doing this matrix algebra. Okay, now one thing which I haven't covered yet is that quantum computation is typically reversible, and so the question arises here, what does it mean in a coalgebraic setting? So reversibility of these kind of things is captured by the requirement that it's a unitary map, right? It's invertible, and its inverse should be its adjoint transpose. And what would this mean for coalgebras? Actually, I have a partial answer to this. Recall that the coalgebras I'm looking at are maps from x to mx, and mx are functions from x to c, where these had finite support. So each cx I'm currying here had finite support. Now I call this swappable, such a coalgebra. If I swap arguments, then I also have finite support. And this is precisely what Samson was describing this morning as locally finite relations. So locally bifinite relations, yeah, precisely. So that you have finiteness in both arguments. Why do I need this here? I define an involution on a set of coalgebras by underlining. I swap arguments, and I also do conjugation. This is the conjugation of complex numbers. Now, it's not very hard to see that this makes this set an involutive semi-ring. And over an involutive semi-ring, you can say what is a unitary matrix, namely a matrix which, when you diagonalize and then apply this involution, well, that's your adjoint transpose. And so, call such a matrix of swappable coalgebras unary if it's an adjoint transpose is its inverse. And the result I have then is that if I have a matrix which is unitary, then the resulting map in vector spaces is also unitary. And so this is nice. but it's not as nice as I would like it to be. There's also an obvious question, does the converse also hold? So if you have a unitary map here, what does it say about the coalgebras that you're using? I don't know the answer to this. Maybe this swappability is too strong as a condition, and I think I simply need more examples to really understand what's going on here. But there's still some.
If the set X is finite, then it follows.
Yeah, I haven't looked at it.
Even then.
I haven't made the distinction whether it's finite or not. That could very well be an important issue. Well, thanks. Thanks for the suggestion. So this is bringing me finally down to Turing machines. What we have so far is, so quantum walks on this line, they use two auxiliary states, up and down. These states, they reappear as in this monad, but also in the 2x2 matrices. Now the next idea is then to use this way of thinking about this to describe Turing machines as walks on a line, so to say. You have a head that's walking on a line, and you have a number of auxiliary states that steer the processing that's going on. These auxiliary states will be captured then by this n in the kind of in the matrix description or in the monad description. And this works at least for a simple example, but it's hopefully an exemplary proof of how this should be done. Let's look at a very simple Turing machine, a non-deterministic one. So I have three states, and the notation here is if you read 0, write 0, step right. Okay. So what this does, if it reads a bit, it can remain in this state. But if it remains a 0, it can also decide to move to state 2. And this is non-deterministic, so it can make two moves here. And so if you consider this as a final state, this machine accepts states which have at least two consecutive zeros. How do you describe the tape then? Well, the tape, I consider the tape for convenience as stretching in 2 dimensions. So I take the integers for this, and the tape itself is a function telling at each position which bit there is, together with the position telling you where you are on this tape. Now there are 3 equivalent descriptions of Turing machines using the finite powerset monad, because I only have finite non-determinism. So in this, let's say, Julia Kemper style, this endomap style, like this, or as a coalgebra like this, because I have 3 states now, or I can do this as a 3x3 matrix. And let me give you one example. I'll use the second one, and then it looks like this. Again, it's a bit notation, but hopefully can steer you through a bit. T is the function, the tape, and P is the position. So I should produce a triple. And each of the entries tells me from state I what the successors are. So from state 3 there are no successors. From state 2 I can only go to state 3, and then I increase the position, and it's only possible if at that position I had a 0. You see how you encode this. Once you get the idea, it's fairly straightforward how to do this. And so there is a bit of fiddling in with these projections and co-projections and where to put everything.
In the tensor product description, what is that tensor product?
It's a tensor product in the category of joint semilattices.
Yeah.
So remarks, this qubit action fits in a coalgebraic setting via this monad construction. And this provides a more uniform state-based description of these kind of things. And also makes quantum computation more discrete, because these coalgebras simply live in sets. And I don't need the whole machinery of vector space or even Hilbert spaces for doing this. It's not clear, I should be careful here, it's not clear how complete this description is. I've covered one example, and hopefully in a reasonably convincing way, but I have very cautious claims about what you can do in general. Now, Turing machines is coalgebraic, and the coalgebraic Turing machine description provides you then genericity in the type of computation. I haven't really stressed this, but the monad T was a parameter in this, so you can replace it by a probability in the distribution function, you get probabilistic Turing machines in principle. So that's very powerful. The transition can be done via matrix composition, so Kleist composition, so you can do it fairly algebraically, and you can use the whole linear algebraic toolbox in this. So what do I see as future work then? So try and use maybe spectral decomposition, calculate eigenvectors for these matrices, and see if they correspond to maybe fixed points. It's not clear, before I get any questions from this, whether this really works or not. The ring that you're working over has to be sufficiently complete to be able to solve equations over this. And what this would mean for coalgebras, I don't know. This is an interesting question in itself. Elaborate more examples, and especially look at this swappability and unitarity issue. And maybe also include measurement in this coalgebraic framework, because I only did transitions so far, but I have some ideas how to do this. But that would take too far, and I'm close to the end of this is the end of my talk, actually. Thanks.
Well, thanks for the nice talk, and thanks for staying well within time, so we have time for questions.
So, have you looked at doing quantum Turing machines then?
No.
Seems an obvious putting together of ideas.
Yeah. I should really look at how that possibly fits in. Yeah.
Because I mean, there have been interesting questions about sort of the name, whether you have. So in some sense, you have classical control, and or do you have some kind of quantum control? And there could be this could be an interesting perspective on those issues.
Yeah, of course, what you could do is apply the quantum monad that came up here in describing the Turing machines as a parameter in this Turing machine. And I don't know. Right, so formally things can be done, but I have not really looked into it, so I should not make any claims.
In physics, the name of the game of these random walks is to get the limiting state.
Yeah.
And there is some work of Bart Jacobs and Mese and these people. Yeah. Have you a chance to use some methods here to get actually the limiting state?
I guess the same methods that are used in physics can be translated to this framework, but that doesn't add anything. But typically, what this coalgebraic framework offers you is notions like bisimilarity, to reason about these kind of things. When are two states bisimilar, or you get a modal logic for free in a certain sense to reason about these kind of states. And I guess that could be a contribution to what's happening in physics. But again, that all still has to be done. It's wide open.
Other questions? Yeah.
Follow up to what you just said. How about taking coalgebraic logic of this function that you described?
Yeah.
How would it compare to the quantum logic?
I have not looked at it. Again, quantum logic for these functions I have not looked at. Also, I don't know what the final coalgebra is. Right? So if the function T or the monad T has a final coalgebra, let's call it Z. My first guess would be that Z to the power n is the final coalgebra of this adaptive monad, and I haven't checked it.
Could it provide different field to quantum logic or like different version?
You do it then.
There's no reason on the face of it why it should be, well, I'm not sure about the quantum case, but it looks like you get a sort of modal logic embedded in the classical logic in
Yeah.
the usual way, as long as you stay in set-based functors. I don't see why not.
But again, I haven't covered measurements, because
Right.
measurements
Yeah.
will introduce a typical quantum phenomena.
I see no further questions, so let's thank the speaker again.